Hello and welcome to the intermediate presentation of my thesis, which I split 80-20 between praxis and theory. The theoretical part covers what I have dubbed game space analysis, a method which represents existing game spaces as graphs. The basic elements of any graph are simple. There are vertices and edges which connect them. Combining these simple elements can yield structures of varying complexity, which can be analyzed mathematically and statistically. That is why graphs are a versatile model for many things. But how can it be done for game spaces? Let's look at an example. This is the plan of a fictional house. To represent it as a graph, we can substitute its rooms for vertices and the doors for edges. Once we have the graph, we can measure its structural properties. For simplicity's sake, let's focus on the outgoing edges from each vertex, the so-called out degrees. In the example, each vertex has between 1 and 5 of them. We can interpret the value as a measure of how much a room serves as a hub. We can also adjust the graph's visualization to account for our findings. Room number 2 now reveals its function as a hub very quickly. Of course, the result was predictable in such a simplistic example, but it works the same way with more complex cases and measures. The example also only covers one of many ways to create a graph from a game space, which is why I described multiple approaches in the thesis. Which one is best suited depends on two fundamental aspects of the sample. The first concerns the size of the observed game space, which I call the scope. Do we look at a single house or an entire island? Generally, the larger the scope, the more data is collected. The second aspect is the size of the collected data points, which I call granularity. Does a data point represent a room or a whole city? Again, the more granular a sample is, the more data is recorded. Initially, I wanted to analyze the level from Dishonored 2, but dealing with a 3D world containing both exterior and interior spaces was difficult. The lack of clear spatial boundaries in some areas made it hard to interpret my observations. So I settled on the 2D platformer Rain World and focused on the structure of connections in the outskirts region of the game. To draw the graph and calculate the measures, I tested different software and Python libraries such as NetworkX, SOCNet, and Gephi. Gephi finally convinced me with its readable interface, directly accessible datasheet, and versatile visualization options. In my analysis, I compared two versions of the region, one from the beginning of the game and one from later when fast travel is made available. The following slides show differences between the two versions in terms of critical path between key locations, path choices offered in each scene, the contribution of each scene to connecting all others, and the presence of subregions separated by point of no return. For more details, consult the finished thesis. Now for the practical part. The idea is to turn a graph into a game space, essentially an inversion of the theoretical part. It is also an exercise in procedural content generation, which I wanted to do in 3D. Initially, I planned to use Blender, Houdini, and Unreal 5, but once I realized that AutoMesh allows using Blender's geometry nodes directly in Unreal, I ditched Houdini. The topic I chose for the procedural content generation was the labyrinths of Knossos from the Greek mythology. Aesthetically, I took inspiration from the actual ruins in Knossos, abstract paintings, and the tactile quality of bare stone walls and tombs and temples. My playground scenes leaned a bit too heavily towards horror, but conveyed some of the sense of mystery I would like to evoke in the final version. Now let's discuss the pipeline for the level generation in Blender. At the moment, it uses the following steps. First, I use the Python script to generate a base mesh. It spawns vertices, which are then positioned and randomly connected by edges. All these vertices then receive custom attributes. The result is an input graph consisting of vertices and edges and their further specifications, not dissimilar to the graphs from the theoretical part. Then, a geometry node group generates the actual level based on the information from the input graph. In this process, different categories of input meshes such as doors, floors, decorations, etc. are assembled to create the final rooms and hallways. The first iteration of the pipeline aimed to generate a circular labyrinth, but I had trouble implementing the necessary trigonometry. Therefore, I switched to a grid-based system. From then on, it expanded steadily. The next step will be taking care of automated texturing, and after that, I will create additional modular assets to feed in and design reusable materials. The plan for the remaining time is to finish all practical work by the end of the year, write the documentation in parallel, and then take the last week to correct minor mistakes in the text. So that's it. Thanks for listening to this presentation, and good luck with your work during the final weeks.